All right, welcome to the Explainer. Today we're going to decode a kind of genius that's hidden all around us. It's like a secret code written right into the living world.
Okay, just look at this thing. It's called the RoboBee. I mean, it's a marvel of micro-engineering, right? It flies with the same precision, the same grace as an actual insect. And yeah, that's an incredible achievement for the engineers who built it. But if you look closely, doesn't its design seem a little familiar? What if I told you the real blueprint for this little guy wasn't drawn up in a lab?
Yeah, because that's the big idea we're diving into. What if, for all of our biggest, most complex challenges, nature already holds the answer? Not from a few years of R&D, but from billions of years of trial and error.
So let's get into it. The first and maybe most obvious way we learn from nature is by just copying its brilliant hardware. We see something in the wild that works, and we just try to copy its shape, its function.
And I mean, why wouldn't we? Just think about the timelines for a second. We've got maybe a few hundred years of modern engineering under our belts. Nature, it's had almost 4 billion years. Every single living thing you see out there is a successful product from an R&D program where the prototypes were tested in literal life-or-death situations. Talk about high stakes.
And this is where it gets really incredible. These kinds of solutions, they're not rare, they're everywhere. Take a look at this. The same fractal pattern that a simple leaf perfected to move water and nutrients around, well, that's become the blueprint for our most efficient networks. We're talking everything from city water pipes and power grids to the way data itself flows across the internet. And sometimes nature's solutions are just wonderfully weird. Case in point, the flick-flack spider. This little guy lives in the desert, and when it needs to get a move on, it doesn't just run, no. It does somersaults. It literally turns itself into a wheel to get away.
So, of course, engineers at a company called Festo saw this, and working with the professor who discovered the spider, Ingo Rechenberg, they built a robot that does the exact same thing. It walks on 6 legs, and then, poof, it curls up and rolls away. But for Professor Rechenberg, this was just scratching the surface. He wasn't just interested in what the spider could do. He was obsessed with the deeper question of how it got that way in the first place.
And that question, well, it brings us to a whole other level. This is where it gets really profound. Instead of just copying the finished product, what if we could copy the creative process? What if we could actually harness the raw power of evolution and use it as an engineering tool?
And that was exactly the passion that drove Professor Rechenberg. See, long before he even found that amazing flick-flack spider, he was already looking at evolution differently, not just as a history book of things that used to exist, but as an active design method, a process we could use right now.
Okay, so picture this. The year is 1964. Rechenberg is at the Technical University of Berlin, and he's setting up what's about to become a legendary experiment. People now call it Darwin in a wind tunnel. His big idea? To see if he could actually make an object evolve, right there in his lab. And the experiment itself was just beautifully simple. He took this metal plate, right? It was made of a few strips connected by joints that he could adjust. And the goal was super clear. Find the one single shape that has the absolute minimum wind resistance, or drag. He started off with this kind of random zigzag shape. And here's where the genius comes in. He perfectly mimicked evolution. First, he'd make a tiny random change to one of the joints. That's the mutation. Then he'd turn on the wind tunnel and measure the drag. If the new shape was better, less drag, he'd keep it. That became the parent for the next try. If it was worse, he'd just toss that change and go back to the one before. That's selection. And just look what happened. Generation after generation, over and over, that jagged plate slowly evolved itself. Step by step, it smoothed out into an almost perfectly flat line. It found the optimal shape all on its own. So what Rechenberg created right there in that lab was this incredibly powerful new technique. He called it an evolution strategy. It's basically a way to let a design discover its own best solution, just by applying that simple but relentless logic of evolution. Mutate and select. Over and over and over again.
And this method, it can come up with results that no human engineer would ever think of. I mean, check this out. His colleagues later used the exact same strategy to optimize a nozzle for a steam jet. They started with a totally normal, standard cone shape, but after 45 generations of evolution, it had morphed into this, well, this bizarre bulging thing. It looks weird, right? But guess what? It worked. Efficiency shot up from 55% to almost 80%. I mean, that is a spectacular improvement for a shape that just completely defies all normal engineering instincts. Okay, so we've seen how we can copy nature's hardware, right? And we've even hacked its software, that creative process of evolution. But there's one last level to go, the biggest one yet. And that's learning from the principles that govern entire living ecosystems.
And this chart, man, it just lays out the difference so clearly. Look at our world, the technological world. We run on fossil fuels, which is a finite stock. Our whole system is linear. We take stuff, we make stuff, and then we throw it away. And because of that, our systems are often really brittle. Now look at nature's world. It runs on the sun, a constant flow of energy. It's totally circular. Everything gets recycled, and it's incredibly resilient, always adapting, always reducing waste. And this right here is what that economy looks like in action. It's beautiful, really. The sun provides all the energy. Then you've got your producers, like plants, that turn sunlight into stuff. Then consumers come along and eat the plants. And when anything dies, plants, animals, whatever, the decomposers break it all down into nutrients that the producers can use all over again. You see, nothing is wasted. The waste from one part of the system is literally food for another part. It is the ultimate sustainable model. Now, to really understand how these natural systems are all around us, not just in some distant jungle, I want you to think about one number, just 2.5 million. What is that? Well, that's the estimated number of ants on planet Earth for every single human. For you, for me, for everyone. It's a staggering thought, isn't it? It kind of makes you realize we're not just living in our cities, we're living in their cities too. We don't have to go searching for these complex systems. They are operating right here, literally under our feet. I mean, check out this research from Dr. Amy Savage in New York City. She decided to study what was living in the little green medians on Broadway. You know, those strips of dirt in the middle of the road. She figured she'd find, a few common pest species of ants. But what she actually found was a thriving, diverse ecosystem with 24 different species. And these ants, they weren't just hanging out, they were working. They were providing a crucial service to the city. Researchers did the math and figured out that these tiny crews, they clean up almost a ton of our dropped food waste every single year. To put that in perspective, that's like 60,000 hot dogs just on Broadway. They're basically a living, self-regulating, distributed waste management system, and they do it for free. So let's just pull this all together. We've been on a bit of a journey here, right? We saw we can borrow nature's hardware, the amazing forms and functions, like that spider wheel or the leaf's veins. Then we can hack its software, the creative process of evolution itself, to find solutions we could never imagine on our own. And finally, we can adopt its entire operating system, those core principles of a circular, resilient, solar-powered world. So you see, this is about so much more than just building a better robot or a slightly more efficient nozzle. It's a totally different way of thinking, a fundamental shift in how we solve problems. Nature is offering us the blueprint, the creative process, and the operating manual, all for free. So the real question left for us is, what should we learn next? Because the deeper we look, the more we start to realize something pretty profound. The most advanced technology on this planet isn't made of silicon and steel. It's made of cells, and it's been all around us, just waiting for us to finally learn how to read the instructions. Thanks for joining me on this one.